special pleasure to have Clancy Rowley today from Princeton. Princeton is also where he got his undergraduate degree and then moved on to California to get a doctoral degree from Caltech. And Clancy has accumulated lots of awards, NSF Career Award, an Air Force Young Investigator Award, and he's also a fellow of the American Physical Society. He's an expert in dynamical systems, control theory, model reduction, Koopman theory, and he's going to tell us today how to find simplicity in complex flows. So Clancy, over to you, and welcome.
Thanks so much. It's a real pleasure to be here. So I thought I'd start out with an example to motivate what I'm going to talk about today. And this is an example I did many years ago when I was a graduate student. And the goal was to look at this flow past a cavity. And this flow, I'll play a little movie here. So the flow oscillates. If you look at the top movie, that's the natural flow. So there you get a little shear layer flapping over a cavity. And this produces a lot of acoustic waves.
We can actually not see the movie.
Oh, really? Oh, no.
Are you skipping the...
It's playing in my window, but let me try.
Oh, here it is. Yeah, it's... Yeah.
Well, but that's okay. You know what? Let me try this. What if I just share my whole window here instead of that one screen? How do I share the whole window here? Desktop. Okay. And now let's try just playing. Now do you see the movie?
Perfect. Yes. Thank you.
Okay. Good.
All right.
And can you see my pointer?
Yes, we can see the pointer now. Yeah.
Oh, great. Okay. So excellent. So, all right. So here's this movie of this cavity flow. You see the shear layer flapping up and down. And when this flapping hits the back corner, it makes a lot of acoustic waves, which interact with the shear layer and create this resonance that you see here. Okay. So we wanted to control this because this happens in vehicles like your car. If you open the sunroof or the window, it can buffet like this. Aircraft have this phenomenon if you have a wheel well or like a bomber, a weapons bay has this. So we wanted to control this and remove these oscillations. Well, we like model-based control. So if you do model-based control, this full system has 2 million states. So this little simulation I did many years ago had 500,000 grid points. There are 4 flow variables, so that's 2 million states. And that's just too big for at least at the time, for our resources to design a controller for a system that big. So what we did was we developed a low dimensional model with only 2 states and designed a controller based on that. And the bottom figure shows how that controller works. So let's play the movie again. And what we were doing, we were sensing the pressure at the back wall here, putting that into our controller, and the controller was providing a signal to an actuator, which here was just a little vertical body force. So if you watch that little circle, you'll see little things, subtle things happening to this flow. So that's our actuation. There's feedback loop here, and we're able to actually stabilize this shear layer and eliminate these oscillations completely. And it's a pretty low Reynolds number flow, okay, so we were able to do this. So when you first see this, you might think, wow, that's amazing. 2 million states down to 2 states. How in the world is that possible? And to get anything useful with only 2 states. But when you look at it a second time, you think, well, actually, that's not so surprising at all, because when you look at the movie, the main feature you see is oscillation, right? This is flapping up and down. And oscillations, we know, can be modeled very easily with 2 states, like a pendulum. If you take the angle and the angular velocity, those are 2 states, and those you can write easy equations of motion that describe that oscillation. So that's really all that's going on here with this model, is we're describing this as an oscillation with 2 states. But this is quite a powerful tool, because then it allows you to use other techniques like control design to design this feedback controller to stabilize this. Okay, so one of the themes I'm going to show is some procedures for getting these models, these very reduced order models, in a general way. Okay, and here's some flows I'll look at as little test problems. So the first one is a linearized channel flow here. So it's flow in a box. The second is a jet and cross flow. And then the third is a T-junction, and the fourth is a separation bubble. Okay, so let's start with the linearized channel flow. And the technique I'm going to show here is the proper orthogonal decomposition, which is POD, and Galerkin projection. And it's sort of a basic technique that a lot of this model reduction uses. I'm sure many of you are familiar with this technique. but here's just an overview of what it is. So let's say we have some high dimensional data here. There are these little points. These little data points are points in some, it's supposed to be high dimensional space. So of course, it's only drawn in a 3-dimensional space. And the idea was we want to project these onto some low dimensional subspace. So that's the blue plane that's labeled as S here. Okay, so how would you project the dynamics? So if you take one of these points, dynamics give you a direction in which that point should move. Well, that direction might not be in the plane, in the subspace. So all you do with projection, Galerkin projection, is you just project that vector onto the subspace. Very simple. But the point I want to make here is actually there's really 2 choices that are going on when you do this. The first is, of course, the subspace S, the blue plane. You need to decide what subspace you're going to project onto. But the second is that gray line, the direction of projection. Now it's easy, the natural thing to do is choose the gray line to be orthogonal to the blue plane, at least if you have an inner product that defines what orthogonal means. But that's not necessary. In fact, you might do better to project, say, along that green direction. And you get different dynamics. It'll be the same subspace, the same data, the same high dimensional dynamical system, but different low dimensional dynamics. And in this case, the green line seems to better fit the data. This is just a cartoon here, but this is showing that you really can get different dynamics with different directions of projection. And in some cases, that can be quite important. So there are 2 choices here, subspace and the direction of projection. Okay, so what is POD? POD lets you determine the subspace, the blue plane, from data. So it finds a subspace of a given dimension you specify that best fits the data in the sense that it minimizes the error in the projection. So in this case, it gives you directions. So these arrows denote directions, V1 and V2. You could think of those as kind of the principal vectors of this ellipsoid that your data spans. And those 2 vectors will span the subspace S. So that'll define the subspace S. And those vectors in POD are called POD modes. This is the same as principal component analysis, if you haven't heard the word POD. So the word of caution is that these modes are optimal for capturing the data, but they might not be optimal for capturing the dynamics. And the reason is that low energy directions or just subtle differences might be very important to get the dynamics right. And to illustrate that, I thought I'd show this shear flow, this linearized channel flow, which seems like it should be quite a simple system to model. So we're going to linearize the Navier-Stokes equations about a laminar parabolic profile. So my pointer's now vanished, but in that picture you see the top wall is a wall, the bottom wall is a wall, the side walls are all periodic, and there's flow in the direction of the arrow. And all I'm going to try to do is model the evolution of a particular perturbation, the one you see there. So there's a little perturbation in vertical velocity, and you see the flow parameters there. So what happens in this flow? Well, actually, Peter Schmidt has studied these flows for a long time and was one of the people really to identify this as a really important mechanism. This system is stable. This linear system is stable, but you get this perturbation before it decays away. It grows a large amount. I mean, here by a factor of 35. This is the Reynolds number 2000. So you see it eventually decays. The system is stable, but first it has this large transient growth, and you see the structures that emerge there, pointed to by those arrows. So all I'm going to try to do with the low dimensional model is capture this phenomenon, this large transient growth before the decay, just for this one perturbation. So if you gather all that data and then compute these POD modes, you find that the first 5 modes capture over 99% of the energy in this flow, and the first 10 over 99.9%. So this looks like POD should work beautifully for this flow. I mean, 5 modes should work great, 10 modes even better. But let's see how this works. So if we take the first 3 modes, which you see capture also the very large share of the energy, you get this little kinetic energy growth that's shown in the red curve, which is nowhere near the factor of 35 growth that we see in the full system, which is the black curve. So this didn't work so well. Well, what if you take the first 5 modes, which captured 99.7% of the energy? You get the same curve as the red curve. It doesn't work well at all, even though these modes captured nearly all the energy, 99.7%. Well, here was what my patient grad student found, that if you take the first 3 modes and then also add the 10th mode, which you see there, okay, now you get the green curve, which has at least better kinetic energy growth, still does some funny things at later times. But if you take those, the first 3 modes, the 10th mode and the 17th mode, a very low energy mode, then you get the blue curve, which actually looks pretty good. It's not perfect, but it's a pretty good model, matches that black curve pretty well. So what have we seen? This, a model with 5 modes, if you take modes 1, 2, 3, 10, and 17, that works much better than a 5-mode model with the most energetic modes. So, you know, the conclusion is that some low energy modes, like modes 10 and 17, can be very important to get the dynamics right. And you can't just naively use the most energetic ones, even if they capture a huge fraction of the energy, like over 99%. It does not always work well. Well, this is a little bit frustrating. You'd like to have a method that works a little better than this, than needing to hunt around and find low energy modes. So what went wrong here, you know, as we said, the most energetic states are not always the best ones to keep. And some states that have small energy can have a big effect on the flow. So in control theory, these concepts have names. They're known as controllability and observability. And the most controllable states are the ones with large energy. The most observable states have the largest sensitivity. So there's a beautiful method called balanced truncation that was developed by Moore and presented in 1981, in which you can determine a change of coordinates in which the states that are most controllable, the most energetic, are also the most observable. So you're the most sensitive to those. And then if you change those coordinates, then it's obvious what to do. You just truncate the states that are least controllable and observable. And there's a method called balanced POD that is an approximation of balanced truncation that works, that's computationally tractable for high dimensional systems. So if we try balanced POD, oh, and what does balanced POD do? Well, remember from the very first slide I showed, there are really 2 things you need to decide when you do this projection. You need to decide on a subspace and a direction. So POD gives you one of these, the subspace. It doesn't give you the direction. Balanced POD gives you both of these. It gives you a subspace here spanned by some modes phi j. That's the kind of flat, the horizontal plane shown here. And it also gives you some modes psi j that determine the direction of the projection. That's those span the inclined plane there. And you can see you project along the direction orthogonal to that plane. So that's the geometry of this. So how well does this work? Well, it works much better than POD. If you look at this black curve is the original, the full system's energy growth. You see growing to a factor of 35 of the original energy. The brown curve shows a 3-mode POD model that we showed earlier with just a tiny energy growth. Well, if you take even a 2-mode balanced POD model, you get the red curve, which is pretty good. And a 3-mode model nearly perfectly captures the energy. The only differences are at the very early times. And if you take more balanced modes, you get a better and better model. So this balanced model works much better, at least for this system with the large transient growth. This shows the energy. For this linear system, you can look at norms and you can see if you want to get the first 5 POD modes perfectly, you need an 8-mode balanced POD model. You need to keep 23 POD modes to get to correctly capture the first 5 POD modes with your reduced order model. Okay, another thing that controls people like to look at, a convenient tool, is Bode plots of frequency response. So this shows the frequency response, at least the maximum singular value of these models. And on the left, you see the POD models. And the feature I want you to see here is these peaks, these spurious peaks that happen in these POD modes. And there's a variety of models keeping very different modes there, but they all have these spurious peaks. These indicate eigenvalues that are really close to the imaginary axis. And these are not going to be the best models, because if you perturb these models a little bit, those eigenvalues may be unstable. In fact, in many cases, these models are unstable, the POD models, where the original system, the linear system we know was stable. It had large transient growth, but it was stable. On the right, you see the frequency response of the balanced models, and these don't have these features. You capture more of the features of this Bode plot as you keep more balancing modes, but you don't get these funny spurious peaks. So in this sense, these balanced models are more robust than the POD models. Okay, so that's all I want to say about this first part of the talk. And the lesson learned is that even if you have POD models that capture, POD modes capture a huge fraction of the energy, even over 99%. And POD can perform surprisingly poorly at getting a reduced order model. And this bad behavior is typical for non-normal systems with this large transient growth, as happens frequently in shear flows. And the reason is that some low energy directions, low energy perturbations you can be very sensitive to that. They can be strongly observable. Okay, but if you use a method that balances these effects of controllability and observability, then these techniques perform well. Okay, so that wraps up the first part of this talk. Next, I want to move on to discuss this jet and crossflow. And the technique that I'll show there is dynamic mode decomposition and Koopman modes. So this, I got started in this problem with this problem here that actually Peter Schmidt worked on with some folks from KTH. So they were looking at I was not involved in this work, but they were looking at the flow, jet and crossflow here. So at the left, you see a picture of an instantaneous snapshot of this flow and these flow structures that are in the shear layer of this jet. You also see some near wall structures in the little gray iso surface which has a couple of bumps in it, and you see the blue and red patches of vorticity leaving near the wall. So these are some features of this flow. And what these folks did is they found an unstable equilibrium, not an easy thing to calculate, but they found this and they linearized about this unstable equilibrium and wanted to see how well these eigenvectors and eigenvalues described the full nonlinear flow. So they compute these global modes, these eigenfunctions, and compared the frequencies of those with observed frequencies. And what they found was that the mode that coincides with these shear layer structures you see along close to the jet are pretty well predicted, the frequency within 20%. But the near wall mode was way off. The frequency was way off, a factor of 2.5. So the conclusion was this linearization about this didn't really work very well for predicting the frequencies. Okay, so what did we do with this? Well, we took this technique that Peter developed and presented at APS in 2008 called dynamic mode decomposition. I'm sure many of you are familiar with this, but I'll just say what it is. So it's decomposition defined by an algorithm. You collect a bunch of snapshots of your data at subsequent times, 0, 1, 2, etc. And you assume that these data are linearly related. So there's some matrix A that can take you from the state at time k to the state at time k plus 1. And then you can use a clever Arnoldi-like algorithm to approximate the eigenvalues and eigenvectors of this matrix A without ever computing the matrix explicitly. You just know these x naught, A times x naught, which is x1, A squared times x naught, which is x2, etc. And you can use this algorithm to find the eigenvalues and eigenvectors of A, at least approximate them. Okay, so a hitch is that typically dynamics, at least for the Navier-Stokes equations, are nonlinear, and the linear assumption does not hold. But let's see how this method works on this data set here. So if you just take snapshots from this full simulation and compute these DMD eigenvectors, DMD modes, you see this, the most high energy one has this frequency, non-dimensional frequency 0.14, which perfectly matches the frequency from the full simulation. And the structures look quite reasonable. You see these structures in the shear layer. There was also a low frequency mode, which also nearly perfectly matches the frequency observed in the full data set. So this actually worked beautifully at finding these structures in a way that the linear stability theory did not work nearly as well. Okay, so what happened here? Why did this work? So the linearization didn't capture the right, linearization about the equilibrium didn't capture the right behavior, but the DMD modes did capture the right frequencies and good structures. But DMD was somehow based on an assumption that the flow is linear. So this kind of seems contradictory here. Well, it works in this case because there's a linear system that fit the observed behavior, which was, again, kind of harking back to the first example, oscillations at a few frequencies. So there was a linear system that captured that reasonably well, and DMD found that linear system. So a question I'd like to pose is, can DMD say anything about truly nonlinear systems? And it turns out that it can. And we'll look at something called the Koopman operator. So what is the Koopman operator? Well, it's a linear operator that describes the full dynamics of even a fully nonlinear system, but not through linearization. So I'll show you how it works. So let's say we have a nonlinear system, a discrete time system here, xk plus 1 equals f of xk. So we're going to consider functions of the state x. And the Koopman operator will act on functions of x, like complex valued functions of x. So if you take a function g of x is a complex valued function, u will map g into a new function ug. And ug at x is just g of f of x. That's just composition. That's all this operator is, composition with f. So this is a linear operator, because if you look at u acting on the function alpha g1 plus beta g2, that's just alpha u of g1 plus beta u of g2. That's how function composition works. So if it's a linear operator, it could have eigenvalues and eigenfunctions, lambda j being the eigenvalues and phi j being the eigenfunctions. Now it turns out that DMD can be can compute. What DMD computes for a nonlinear system like this is something called we call Koopman modes, where if you take a vector valued observable function, say a vector of such functions, you could expand each component of this. Sorry, I messed up there. You could expand each component of this as in terms of these eigenfunctions, assuming you have enough eigenfunctions. And that would have coefficients vj, component of vj. If you stack these up into a vector, those coefficients become vector valued. And those coefficients are the Koopman modes that are actually calculated by the DMD algorithm. So this DMD is really tightly connected with this Koopman operator. Okay, one really interesting feature of this Koopman operator is that it lets you determine linear models of a system without actually linearizing the system. And I want to show you how this, what I mean by that. So linear systems are very nice. We have lots of techniques for analyzing them, designing controllers for them. We can even deal with systems with very high dimension, like we looked at in the first part of this talk. But real systems, are not linear usually. So these Koopman eigenfunctions determine a very useful set of coordinates in which the nonlinear dynamics look linear. And I'll show you exactly what I mean by that. So let's take this little map here. So a little two-dimensional map. It maps x1, x2 into what you see there, lambda x1, comma mu x2 plus that thing times x1 squared. So that system has an equilibrium at the origin. It's easy to see that if x1 and x2 are 0, then they'll stay at 0. And then it has some invariant manifolds you see there. And that little parameter c determines sort of how nonlinear it is. Notice that if c is 0, there's no coefficient in front of x1 squared. You just get a linear system. But if c is non-zero, then you get some curvature to that invariant manifold, and it becomes a nonlinear system. Well, the system has Koopman eigenvalues and eigenfunctions. The eigenvalues are just lambda and mu, those parameters in the system, and the eigenfunctions are what you see there. And notice that the 0 level set of phi mu is exactly that invariant manifold. And if you look at other level sets, you get these gray lines. These are level sets of those two eigenfunctions. And these, you can view this as forming sort of a curved graph paper, which can determine then coordinates of the state of the system. And if you use those coordinates, just the values of those Koopman eigenfunctions, just map to that little nonlinear change of variables at the bottom, in those coordinates, the dynamics are linear, and they're even decoupled. So z1 maps to lambda z1, and z2 maps to mu z2. So these Koopman eigenfunctions determined a very helpful set of coordinates that just linearize the system. You can think of this as like diagonalization, but for a nonlinear system. Now, you can't always do this, but if you have enough Koopman eigenfunctions, then you can do this. Okay, so how do you compute Koopman modes? Well, we've seen that DMD can compute these things. So the message here is going to be you need to be a bit careful. This is just how the algorithm works. You can compute these DMD modes. This is one way of doing it. You can compute this matrix A and find eigenvalues of A. Okay, so this is a way of computing Koopman modes. What I want to show you is that this doesn't always work for nonlinear systems. So there's an extension of this where you approximate the Koopman operator directly, and then you obtain these Koopman eigenvalues modes and eigenfunctions. So I should have emphasized on the previous slide that the DMD finds these Koopman modes, but it doesn't actually tell you the Koopman eigenfunctions, which here is what we wanted to find out. So this extended DMD lets you compute these eigenfunctions. What you need to feed it, in addition to the data, is a set of observables, some functions. These are just real or complex valued functions, which will serve as basis functions for a function space, a subspace of a function space on which we'll project this Koopman operator. Okay, so then this extended DMD, which we call EDMD, is just a projection of the Koopman operator onto the subspace spanned by those observable functions. So let's just illustrate this for this example. So here's back to this example we just showed. Remember, you had these two Koopman eigenvalues and eigenfunctions. I just also wanted to point out that if lambda is an eigenvalue, then lambda squared is also an eigenvalue. And lambda times mu is also an eigenvalue, with eigenfunctions just as the product of the eigenfunctions too. It's just a feature of this operator. So let's try to compute these eigenvalues and eigenfunctions using EDMD. The other thing I want to remind you here is this parameter C controls how nonlinear the system is. If C is 0, it's a linear system, right? And if C is non-zero, it's a nonlinear system. Okay, so let's apply DMD to this example. Let's take that's only 4 data points we're taking here, some initial states, and there's the values of lambda and mu that we'll use. Well, if we apply EDMD with this, so we need to say what we're going to measure. So let's say we observe here Z1 and Z2, the full state. Okay, and we'll apply DMD to this, or extended DMD to this. If C is 0, this nonlinearity parameter, then the DMD eigenvalues are spot on, 0.9 and 0.5, which is exactly what we expect, that those are the correct eigenvalues. But if C is 1, so there's some nonlinearity, then the DMD eigenvalues are 0.9, that one's good, but the second one is 2, and that's nowhere close. It should be 0.5. In fact, for this discrete time system, we'd even get the stability wrong, right? 0.5 is less than 1, so that would be a stable discrete time system. 2 is greater than 1, so that would be an unstable discrete time system. So we'd even get the wrong stability of this nonlinear system if C is 1. Okay, so this didn't work very well, and we observed the whole state there, Z1 and Z2. Well, what if we now observe the 3 things, Z1, Z2, and also Z1 squared? And you might say, well, that's silly. Why would you want to, you're already measuring Z1, why would you also measure Z1 squared? If you know Z1, you can figure out Z1 squared. Well, that's right, but the idea is here, these are supposed to be functions of the state, and this is now, so the first function is just the function that returns Z1, takes Z, returns Z1. The second function takes Z, returns Z2. The second function takes the vector Z and returns Z1 squared. So now we have 3 functions in our function space. So it seems silly to add this third variable, but it makes sense if you regard these as functions. So if you take these as the observables, then the EDMD eigenvalues are spot on, right? We get 0.9 and 0.5, and the third one is 0.81, which is 0.9 squared, which is, these are all, actually real, analytically determined Koopman eigenvalues. And okay, so the main point is, so this works well. So the main point is for a nonlinear system, if you do just DMD by itself, it can give erroneous results. It can give you eigenvalues that are not always corresponding to Koopman eigenvalues. And you often need a richer set of these observable functions. So let's try this out on some more interesting nonlinear systems. So here's the Duffing equation. Again, just 2 states here. The states are x and x dot. So y, as shown in the figures, is just x dot. And we've tried EDMD on this system with a lot of data. So we have 1,000 trajectories with 11 points along each trajectory. Just trajectories are solutions of the system for different initial conditions. What basis functions do we use? Well, here we used 1,000 radial basis functions. Here, thin plate splines centered at points at 1,000 different points in the domain, determined by an algorithm, this k-means clustering algorithm. So if we use those 1,000 basis functions, then we find eigenfunctions as shown. So the first eigenfunction is the constant function, and that's always an eigenfunction of the Koopman operator. The second one, reveal, is shown at the figure at the bottom left. Level sets of that eigenfunction. And that reveals these 2 basins of attraction. So this Duffing equation has 3 equilibria. One is unstable at the origin, 0, 0, and then 2 in the, since my pointer's gone, I can't point to them, but they're in the centers of those 2 red and blue blobs there. And those are stable equilibria for this, for positive delta. So the red and blue regions indicate the or sort of demarcate the region, the basins of attraction of each of these equilibria. The plot at the right shows all the points that are mislabeled. So if we use that eigenfunction, that calculated eigenfunction to label the points by which basin, which equilibrium they end up at, the only points that are mislabeled are those green ones that are right on the boundary that are very difficult to sort out correctly. Okay, how about the other eigenfunctions? So the first eigenfunction determined the basins of attraction. The next one determines coordinates in each basin in which the dynamics are linear. So on the left, we're showing the magnitude of, so top left is the magnitude of the second eigenfunction. And this is like a radial coordinate around that rightmost equilibrium at x equals 1. And on the top right, you see an angle coordinate. These are just like action angle variables for this nonlinear system in the base of attraction of that equilibrium at x equals 1. And the other eigenfunction at the bottom shows the same thing for the equilibrium at x equals -1. So these are, just magnitude and complex phase of these Koopman eigenfunctions that determine these nice handy coordinates in which the dynamics are linear. Okay, so this seems to work well, but this is not really an ideal method to use for complicated systems. This example I showed you was a two-dimensional ODE, right? We want to apply these to high-dimensional problems like fluids with, many more than 2 states. And just to show you and even for that two-dimensional system, I used 1,000 basis functions. So if you have 400 states is not a lot for a fluids problem, but if you have only 400 states, if you choose the basis functions for EDMD to be all monomials in these 400 variables up to degree 10, well, that's 10 to the 19 functions, and that's much, much too large for easy computation. So one idea to make this method work in higher dimensions is to use kernel functions. So this is a trick from machine learning. This method, this extended DMD method, only requires inner products in the high dimensional space. High dimensional meaning dimension k, the 10 to the 19 dimensional space. So if all you need is inner products, then you can use a kernel function, which has associated with it a feature map. So there's a feature map that maps you from your state space, 400 variables, to the feature space, 10 to the 19 variables. And you don't ever explicitly use that feature map. The idea is to avoid working in the high dimensional space. Instead you can compute inner products in that feature space by just using a kernel function, which just acts on the state space, the smaller dimensional, 400 dimensional space. And this gives you a potentially huge computational savings, order n, order 400 instead of order k, 10 to the 19. So these kernel functions can be a help. It's still, however, a very difficult problem to determine good kernel functions and good, good sets of basis functions for EDMD. Really a difficult problem as for these high dimensional systems. But here's one trick that you can use to make it a bit more tractable. Okay, so that's all I'm going to say about DMD and Koopman operator. Now I want to shift gears and talk about this T-junction flow. And here the tools I'm going to look at are just stability and bifurcations. But I think this is a very interesting flow that I'm excited to tell you about. There are some features that were very surprising to me, at least. So it's just flow at a T-junction. So it's a common piping element, at these small scales in a lab, bigger scales in processing, and it occurs over. I mean, this practical thing occurs in a lot of situations, even inside your body, in your blood vessels in your body. There are lots of these T-junctions. So this is joint work with Howard Stone and Kevin Chen, who was a student of ours. And this is, I think, before these folks looked at this, I don't think this phenomenon had been seen before. So here's the geometry. There's flow down through the inlet and then flow out through both sides. And there's a Reynolds number associated with this. So what happens in this flow? I'll show you this movie. This is one of Howard Stone's postdocs, Daniele Vigolo, took this movie, and they were looking at the effect of particles in these flows. So those black dots you see in the movie are solid particles, and they were looking at how these impact the wall. These particles are more dense than the fluid. And they thought, well, okay, it'd be interesting to look at what happens if you replace the particles by bubbles that are less dense than the fluid. And here's what they saw. a very surprising phenomenon. They saw these bubbles start to collect near the center of this T-junction. This was very surprising. This is not at all what I would think would happen. I would think the bubbles would just flow out the two sides, but they found that many of the bubbles did not actually flow out the two sides. They collected in the middle. They were sort of trapped. Okay, they vary the geometry, they change the angle. It does depend on Reynolds number. So at Reynolds number 250 at the left, there's no trapping. At the Reynolds number 450 at the right, there is trapping. So very surprising that these bubbles would be somehow trapped. I would never have guessed that. Okay, so we wanted to understand this. So there's been a lot of studies on flow in curved pipes or curved tubes. It's called Dean flow. And you see these centrifugal effects create these two vortices in this flow. I at the left denotes the inner wall, the inner curvature. O is the outer wall, the outer side of the curve. And you see the centrifugal effects just sort of fling the particles toward the outer wall and create these two vortices. So this is a very well-known phenomenon. And we observe similar effects in this T-junction flow. Okay, so here's some three-dimensional features of these. So I'm showing the yellow region shows the Q criterion, which is a way of visualizing vortical structures in these flows. And then the stream tube showed particle traces. And you see some of these particles get trapped, and some of the particles move out of the T-junction. Some get trapped inside these yellow regions. So it's in these, you see the closed streamline inside the yellow region. This is a signature of something called vortex breakdown, which is, has an interesting feature that there's a stagnation point internal to a flow, not at a wall. So we all know what a stagnation point is. If you have a flow impinging on a wall, you'll get a stagnation point somewhere in the middle there that separates the flow going up from the flow going down. But you can also have a stagnation point internal to a flow, which is what happens in our flow here. So the stagnation point is right at the end there. And this is sort of an unusual phenomenon. But it does happen in other situations. For instance, this flow past this aircraft wing, you see the little white cloudy vortex being shed from the little wing, and then it sort of balloons up at the back of as the vortex evolves downstream. So that's this phenomenon called vortex breakdown. And this has been well studied. Here's an experiment by Leibovich in 1978 showing the same phenomenon. The thin vortex expands into a thick vortex like that. And there's a stagnation point right at that location. Here's a study from Phil Holmes in the 1980s, did a study of the dynamics of trajectories in this flow. And you see these stagnation points at locations A and B in this flow. So this is actually what is happening in this T-junction flow. You get a stagnation point internal to the flow, and it's a hallmark of this recirculation. Okay, so we wanted to look at the stability of this system and how it changes as you vary the Reynolds number. And what we find is that for low Reynolds numbers, there's no recirculation, right? This is what the flow looks like for very small Reynolds numbers. As you increase the Reynolds number, okay, the streamlines become more interesting, but still no recirculation. At some point, you start getting those yellow regions, again, are denoting the Q criterion. And this is a way of visualizing the vortical structures. There may or may not be recirculation there, but at some point, these structures grow in size, and one definitely has recirculation inside of them. We didn't focus so much on the recirculation as what happens as you increase further. At some point, you get a Hopf bifurcation, and this equilibrium here becomes unstable, and these structures start to oscillate and warble, and you get even subsequent Hopf bifurcations. Each square there denotes another Hopf bifurcation. Oh, I should have pointed out the three curves are different radii of curvature at the junction. So the junction could have 0 radius of curvature, so just a sharp corner, or some curved wall there at the junction with some radius. So here's just a movie showing the unsteady flow after the Hopf bifurcation. So here's the structure, and for lower Reynolds numbers, the structure is just steady, but for a higher Reynolds number, the structure starts to warble like this and oscillate, and that's what happens at a Hopf bifurcation. You get this periodic orbit. So this is precisely what we observe in the experimental data too. Okay, you can also use this linear stability theory to analyze these structures as they warble. These are the eigenmodes at the frequency of the Hopf bifurcation, showing how this meanders, these structures in this, the red and blue structures you see there. You can also look at the adjoint eigenmodes, which show you where perturbations will most effectively excite that eigenmode. And you see you're most sensitive to places at the wall. So if you wanted to influence that in some way, you could perturb the wall, perturb the flow near the wall there. Okay, so that's the third topic I wanted to show you. So I'll finish with this discussion of the separation bubble. And in particular, I want to talk about a method called the harmonic resolvent, which we've used to analyze this the unsteadiness in this separation bubble. Okay, so here's the problem I'm looking at here. We have a boundary layer, just a Blasius boundary layer, which we then impose an adverse pressure gradient on to cause the boundary layer to separate. We're working with some experimentalists. You see my collaborators down below, Charles Menneveau, Rajat Mittal at Johns Hopkins, and Wen Wu. And we're trying to control this flow and ideally reduce the size of the separation bubble. And there's some actuators you see. We want to ask questions such as what frequency is best to actuate these zero net mass flow actuators. There are several frequencies present in the flow. We want to know how these frequencies interact with one another. So we want to capture these nonlinear interactions between the frequencies that are present in the natural flow and also the forcing frequency that we might impose here. So how could we capture nonlinear interactions between frequencies? Well, I want to say a little bit about what resolvent analysis is. So if we have say a nonlinear system shown there, so what you can do is you can consider perturbations about some base flow. Here I'm denoting the base flow to be capital Q. So one often takes the base flow to be the mean of a turbulent flow, for instance. So you linearize about that. There are the linearized equations, and H prime denotes the leftover terms from the nonlinear part. Okay, well, if you Fourier transform that equation, then the ddt turns into an I omega, and you get this equation down there at the bottom left, which relates the perturbations H hat to the perturbed state Q hat. Okay, so that operator there, the inverse of I omega I minus A, that's called the resolvent operator at frequency omega. And if you analyze that operator, you can look at, for instance, its eigenvalues or its singular values and singular vectors, and those will describe the amplification of perturbations at frequency omega. Okay, so that's how this resolvent analysis works. It's just linearization and then looking at singular values and singular vectors. And this has been used very effectively by two of the main references are down below. Okay, so some difficulties with this is that this is very good at capturing the amplification of disturbances at one frequency, omega, but it doesn't say anything about nonlinear interactions between frequencies. And that's one thing we want to capture here. Also, the perturbations Q prime might be large, and we might be interested in how those larger perturbations evolve. So an idea you can consider is to consider something called a harmonic resolvent. So instead of linearizing about a fixed base flow, capital Q, what if you let Q vary in time? So make Q a periodic orbit. So that's shown in the picture here. Rather than linearize about the red dot, a fixed flow, you could linearize about the black periodic orbit. And then if you're, for instance, if your trajectory is the blue curve, well, the blue curve is closer to the black curve than it is to the red dot. And the perturbations Q prime are smaller than they would be if there were perturbations from the red dot. And in addition, you could capture something about nonlinear interactions. And I'll show you why you get nonlinear actions when you linearize about a periodic orbit. So now instead of writing the full flow Q as a fixed base flow, capital Q, plus a perturbation, we'll let the base flow Q be periodic with some period. And we'll also consider periodic perturbations, Q prime. So we'll expand both of those in some Fourier modes. So NB is the number of Fourier modes in the base flow, and N is the number of Fourier modes in the perturbation. They might be different. You might have different numbers of Fourier modes there. So now if you linearize about Q of T, the resulting equations will couple different frequencies through the base flow. you'll get terms that multiply the perturbations and the base flow, and those multiplications will give you coupling between the two frequencies. So just for instance, if you take just one Fourier mode of the base flow, so sinusoidal base flow, and then two Fourier modes in the perturbations, you'll get coupling terms that look like this. So this matrix at the left is actually the inverse of the harmonic resolvent operator, but you'll see it has a very nice structure. Now what are those things? Well, R sub omega is the regular resolvent operator at frequency omega. So if you take just one frequency, for instance, in the base flow, then this would be just one, you'd have only one block in the left matrix, and that would be the inverse of the original resolvent operator. But now we'll get these coupling terms, and of course, when you take the inverse of that matrix, it'll be a full matrix. It won't even have that block tridiagonal structure. So you'll get a lot of interactions between frequencies, between the different frequencies. Okay, so the inverse of that matrix on the left is the harmonic resolvent, and that'll describe interactions between frequency omega and its harmonics. So, okay, H denotes that harmonic resolvent, and it tells us the response to perturbations at the different harmonics of the frequency of the base flow. And questions we're interested in. So what is, for instance, the input? Now it's a space-time input because it has frequencies in it as well as the spatial variation. What is the input that excites the most energetic response? And then what's the forcing input at a particular frequency alpha that excites the most energetic response at some other frequency, omega? Right now that we have nonlinear interactions between frequencies, we can have interactions like that. And both of these can be answered by looking at H, and in particular its singular value decomposition, or just of one of its subblocks. So I'll show you first on a little model problem and then on the boundary layer problem. So here's flow past an airfoil at a high angle of attack, so the flow is separated, and there's some vortex shedding behind it. Now at the right is shown the spectrum of the vortex shedding, and you see there's a fundamental frequency 2.4, and then many harmonics of that in the shedding. So what we'll do is we want to look at perturbations of this and see how perturbations affect the overall flow. So we'll compare two different base flows. The first is linearizing about the steady, just the mean, which is the standard resolvent analysis. And we'll compare that against linearizing about the periodic orbit with containing 3 harmonics. That's the harmonic resolvent. We'll then compute the SVD of that and compare the response with the observations from the full simulation. So how does that look? Well, at the left is the Fourier coefficients of the full nonlinear simulation. So that's the truth. The middle is the resolvent modes from the periodic base flow, and that looks very similar to the truth. At the right is the resolvent modes from the steady base flow, and that looks actually pretty different. I mean, if you look at it, if the details are quite wrong when you look at that closely. How about at frequency 2 omega? So there are at the left is the truth. In the middle is the resolvent modes about the periodic base flow. And at resolvent modes, we get really just noise. There's not much response there in the resolvent about the steady base flow. So we're really just looking at noise there. At 3 omega, we get similar, very good response from the periodic base flow. And there's just it's just complete noise for the resolvent. Okay, so that's response at the same frequency. How about nonlinear interactions between frequencies? So now if we take that resolvent operator, which is now you could think of as like a block diagonal, or sorry, with several different blocks in it here, maybe 15 blocks if we have 7 harmonics. So 15 times, we have the size of this is actually quite large. Each block has the dimensions of the resolvent operator, and we have 15 by 15 blocks. But we can look at the maximum singular value of each block, and that will tell us how much coupling there is between forcing at a particular frequency. So at the horizontal axis is the forcing frequency, and the vertical axis is the frequency of the response. And wherever you see the darkest blocks, you get the biggest response. So this tells us that forcing at higher frequencies doesn't give us much of a response, but forcing at, say, the fundamental frequency 1 omega, the same frequency as the vortex shedding, gives us a response that couples to many of the different frequencies of this flow past the airfoil. Okay, so finally, let's apply this to this turbulent separation bubble. I described this earlier. There's an adverse pressure gradient that causes the separation. And in these numerical experiments that Wen Wu did, they were forcing at 3 frequencies, the fundamental frequency of this vortex shedding bubble, and then 2.5 times that and 10 times that. And what they observed in the simulations was that if you force at the low frequency, this will shrink the separation bubble, but high frequencies had no effect. And if you forced at the frequency of the separation bubbles shedding, that caused an energetic response at the same frequency. So we wanted to look at this same flow using the harmonic resolvent. And what we did here was we actually did a span-wise averaging of this data. So we had only two-dimensional data, but we looked at 3-dimensional perturbations of this. And we considered this breathing frequency that was identified in the simulations, and we took one harmonic and linearized about that periodic base flow at that frequency. Okay, and then we looked at the harmonic resolvent. Now I'm showing only a quarter of this matrix. The matrix is symmetric, so it has the symmetry, so you can look at only 1/4 of the matrix. But this tells us the sensitivity of this flow to forcing at different frequencies by looking at the maximum singular value of each block. So we looked at 10 harmonics of this. And what we see is that, so again, the horizontal axis, think of that as the forcing frequency. The vertical axis is the response frequency. So that, and frequency 0 is, of course, the mean, the turbulent mean separation. And we see that the mean separation bubble, which is in blue, that's affected by low frequencies. If you force at frequency 0 or frequency 1, you'll have an impact at this. Frequency 2 and 3, you have some lesser impact on the mean separation bubble. But if you force at frequency 10, then 10F, then you have basically no effect on the separation bubble, on the mean separation bubble. Right, so if you, in fact, you don't have effect on any of the flow if you force at such a high frequency. But if you force at frequency F, then you excite an energetic response. The darkest block there is at 1 FL, so you have the biggest response at the same frequency, but also response at twice the frequency and also a steady mean. So we can look at the structures that emerge there too, the singular vectors show the structures that are excited by this. Okay, so this gave us qualitative agreement with observations from the direct numerical simulation, even though we're looking at only span-wise average flow, like that. Okay, so that brings me to the end of the talk. So we looked at these 4 different flows, and we looked at several different techniques for finding simplicity in these flows, ranging from projection of the dynamics to DMD, dynamic mode decomposition, linear stability, and finally, this harmonic resolvent analysis. So I'll wrap up there. I do want to acknowledge all the students and postdocs and collaborators who worked on this, and funding from the Air Force and the National Science Foundation. And that's all. I'd be happy to take your questions.
Great, thank you. Thank you, Clancy, for a very, very nice talk. Big overview, lots of material. I'm sure there's lots of questions. One that actually came up during the talk, I'm going to ask on behalf of Emily Southern. Her internet connection is not so good. So she's asking about on slide 24, when Z1 squared is added to the EDMD, what happens, for example, if you add Z2 squared, or naively adding a whole library of extra functions? So she's thinking in the direction of Cindy.
Yeah, that's an excellent question, really excellent question. So if you add Z2 squared, it won't do any harm. It won't, but if you did Z2 squared instead of Z1 squared, then you actually wouldn't get a benefit. So why Z1 squared? You can still see my screen, right?
Mm-hmm. Yeah.
Okay, so let's, let me just make this bigger so it's easier to see. Okay, so why was Z1 squared the right thing to do? Well, we knew beforehand actually that this was the correct Koopman eigenfunction. The correct Koopman eigenfunction had a Z1 squared in it. And that's why Z1 squared is the right thing to include here. So if you think about, if you have the function Z1, if you have the function Z2, and the function Z1 squared, then you can represent both of these as superpositions of those 3 functions, right? So that's why Z1 squared was the right thing to add here. If you added Z2 squared, that wouldn't help you get this function here, right? You'd still get this one wrong. So yeah, you wouldn't get any penalty if you added that in addition to z1 squared. Well, maybe you wouldn't. I guess you'd still get these three correct. You would get a fourth eigenvalue, which might be wrong because there would be no eigenfunction. The next eigenfunction that would involve z2 squared would be the square of this thing, which would also have a z1 to the fourth term in it, and also z1 squared times z2. So that if you wanted to get a further eigenfunction, the next things you would add would be not just z2 squared, but also z2 times z1 squared and z1 to the fourth. If you did that, then you'd get...
If you add that one, would you then get an additional eigenvalue of 0.25?
You'd get an eigenvalue of mu squared, which is 0.2, exactly.
Yeah,
that's
okay,
exactly
but
right.
if you add only z2 squared, you wouldn't get one in 0.25, you get some crooked one.
You get some crooked, that's right, you get one that doesn't make any sense. So yeah, some of these eigenvalues would be legitimate, accurate eigenvalues, and some would be inaccurate. Yeah.
Right, okay, good.
That's an excellent question, yeah.
If you have any other questions, just unmute yourself, and while you think about one, let me squeeze one in. For the harmonic resolvent, Clancy, you go for frequency to frequency, so input to output, forcing to response, right? But often when we do flow analysis, nonlinear flow analysis, or weakly nonlinear flow analysis, there's actually two paths. One is going through a mean flow, that would be of zero frequency, and one is going directly from perturbation to perturbation. Could you actually separate those two out by using masking matrices or something like that?
Oh, that's a great idea.
By blocking certain pathways.
Yeah. Oh, that's an excellent. I have not even thought about that, but you certainly could. I mean, if you took this matrix and just, so I think you're saying just mask out some of these.
Exactly. Yeah.
Well, that's a great idea.
This way you can do one pathway and then you do the other pathway and then you can decide which one is bigger. They all have to sum up to the same energy transfer.
Yeah, what a great suggestion.
One pathway could suck energy out, while as the other one is actually putting more in. So in net, you get what you showed us.
Yeah, and that would really let you understand in a lot more detail the fundamental flow mechanisms going on.
Yeah, you could dissect it a little bit better.
Yeah, that's an excellent suggestion. Yeah. I mean, I guess in a way we did that by just comparing the, I mean, a very primitive version of that is just to mask out these off-diagonal blocks altogether. And then you're looking at just the plain resolvent. You're neglecting all pathways through the mean flow. But you're saying you could do a much more fine-tuned analysis of that. Yeah. That's a great suggestion. Yeah.
Good. Any questions from the participants? Just unmute the microphone and fire away.
Hello.
Hello.
Andrew Hazel here. I have a question. So following up on what we were talking about the harmonic resolvents, when you presented the comparisons with the, or maybe it was the one before with the T-junction. Anyway, you presented comparisons with the steady cases versus the periodic, and the steady was fairly rubbish. Did you look at the mean of the periodic flow versus the steady? What I'm getting at here is how much steady streaming was there going on, and was that the effect that you weren't capturing with the steady flow?
Okay, let me try to make sure I understand your question. So you want to look at the mean.
The mean of the periodic flow is not necessarily, when you've got nonlinear effects, is not necessarily the same as the steady. The mean of.
That's right. Yeah. So you're saying that the perturbation, say at frequency omega, may affect the mean flow.
Absolutely. It's basically because cos squared can be rewritten as a half plus a half cos 2t. So you get this mean contribution.
Yeah.
Steady streaming or acoustic streaming or anything like that.
I think we did look at that. Of course, that effect would not be present in the linearization about the steady base flow.
Absolutely.
But it will be. There will be an effect there. Actually, maybe you can see that here. Okay, so there is an effect because this is that same flow. I guess I didn't show the plot here, but there is an effect here because this shows if you force at frequency omega, there is an effect on the mean flow here.
Absolutely.
But I didn't plot that picture. I didn't show you what the effect was. but there is an effect there. Yeah.
Okay, I guess I was just wondering if that's the dominant effect, if there's anything else going on, do you know?
Yeah. Well, it certainly has a big singular value, one of the biggest singular values
Yeah.
here. So it may be that is the dominant effect. I mean, to be honest, we weren't so interested in studying the flow physics of this problem. We were more using it as a test problem to kind of understand the tools we were using. But I think that's a good thing to just go back and look at what the effect on the mean was. Yeah.
Okay, thank you.
Yeah.
There is actually, in the meantime, a comment or a question from Jonathan Mestel in the chat. When surgeons make bypass grafts, they typically take a piece of vein and splice it into another vessel. When they make a T-junction, they often observe end-to-side anastomosis. Reblockage occurs in time. This can be avoided by having the incoming tube at an angle or a recommended twist in the third dimension. And I think Andrew Hazel worked on this one too.
Oh, wow.
So can you?
Yeah, I did. That's partly what motivated the question.
Wonderful.
The
Okay.
conclusion I came to there was that one of the dominant effects was you got a massive shift in the position of the time average stress field precisely because of these streaming effects.
Mm-hmm.
So you could get the oscillations would change the patterns, and that was consistent with the directions where they saw this gunk building up. So basically you get gunk building up in your arteries, even though there's a periodic flow near the walls when they have these types of junctions.
Mm-hmm.
Yeah. Good.
Yeah, that's interesting. So you say you break the symmetry by having them come in at an angle. Yeah.
Yeah.
Mm-hmm.
I mean, of course, the real constraint the surgeons have is they just have to fit it how they can. Mm-hmm. So, essentially what they're interested in is straight versus angle. Any precise details is really constrained by the anatomy.
Mm-hmm. Mm-hmm.
Any other questions?
Yeah, Peter, may I ask?
Yeah, Shusong, of course.
Yeah, kind of probably revisit the questions for the first one. So for extended DMD, you introduce these observables. So what in the general case of like thinking the high dimension? So what's the guidelines for choosing the one that works, or whether in any sensor it's kind of optimal one, and how do you do it?
Yeah, I wish I knew. I mean, I think there's no great general procedure for doing that. I mean, to be honest, I mean, I think there are basic things you can do. If you know something about the state space, you could in principle choose good things. I mean, in this example, we knew what the eigenfunctions were, so we knew what terms to choose. Often things that make sense is to include just monomials, like polynomials in the states, just because you can approximate, smooth functions with polynomials. Mm-hmm. So that's a starting point, and that's what some of these techniques like this kernel method. So in this example, we took radial basis functions. We're trying to just describe general functions over this square. So radial basis functions is a reasonable thing to choose in that case. But in high dimensions, you're going to have an awful lot of radial basis functions to choose. So I think it's a very challenging thing doing this extended DMD, this Koopman stuff.
Could it happen that if you do it, you kind of could it, by introducing these extra observables, you can make things worse? It could be worse.
You certainly could, yeah, right. I mean, if you just do it in a haphazard way, you can certainly make things worse. Yeah. In fact, okay. with these kernel methods that I showed, so this is another way. If you're going to just introduce monomials in these different variables, these kernel methods are a very nice way to do that efficiently. But of course, what happens is if you have a really high dimensional space you're working in, like this, 10 to the 19 functions, well, you're going to overfit your data. You don't have that much data. You have many more, say, parameters in your model than you have data points. You're going to fit all the noise in your data and not get a meaningful model. And I think that's part of what you said you can make things worse. Absolutely, you can make things worse by including so many basis functions that you can just fit, just like with polynomial interpolation.
Yeah, yeah.
If you have a bunch of data points and fit an extremely high degree polynomial through it, you'll get nonsense because it'll just interpolate all the data perfectly, but overfit it. Exactly the same thing can happen here.
Yeah, but I have a question, probably can in general, in a similar sense. So with this harmonic resolvent, so if you have a system, okay, flow in which there are a lot of frequencies and low and high ones, and they are also, quite strong or pretty strong. How do you separate the two? Which one you introduce as a linear response, others as a kind of part of the base flow?
Yeah. Well, I think that's a very challenging problem. And I'm certainly not trying to claim that the harmonic resolvent is the solution to every problem. I mean, I'm really considering a pretty simple situation where you have some periodic.
For your specific one, so you choose the frequency, is the shading at the shading frequency or?
Yeah. So, yeah, so maybe if you look at here, there were all these different frequencies that are here. How did we choose this red one? Is that your question? I mean, there are certainly all these frequencies.
In a sense, is a dominant. It corresponds to the peak, spectrum peak, isn't it?
It is the strongest peak, but as you correctly point out, there are many other frequencies here as well. I mean, this is a very complicated turbulent flow.
They really could. Yeah, I mean, here you other harmonics kind of talk to each other through this the components in the treated as part of base flow. But again, there is those other frequencies also talk to each other directly.
They certainly do. Yes.
So it's a nonlinear. That means this is what you described is more like kind of parametric resonance, right?
You could think of it that way, yeah.
Yeah, and then there's just nonlinear one. It's omega 1, omega 2. They can interact to produce omega 1 minus omega 2, for example, not just a sum and the difference with the seeded.
Yes.
Yeah, so there is that part that's nonlinear interaction. That's
certainly,
not in the model,
right? Right. The only interactions we're looking at are interactions between perturbations and the base flow, not perturbations and other perturbations.
Yeah.
Another way to look at that.
Yeah.
Yep.
But if they are strong, can be important, I think.
They may well be important. That's right. Yeah.
Okay, thank you.
Any more questions?
Oh, there's a question in the chat about, I wonder how you think autoencoders might fit alongside the methods you've discussed.
Yeah. Oh, yeah, good one. Yeah.
Are they also suitable to certain problems, or are they applicable to most problems? Well, that's a really good observation. I think autoencoders can be quite useful. In fact, I have a student now who's looked at autoencoders for a problem like this one with the Duffing equation. So, here we're trying to learn a function. We're trying to learn these eigenfunctions of this system. And here in this example, we used radial basis functions that we sort of specified beforehand. But you could also think about training an autoencoder to learn these functions for you. And there's some work that one of my students, Sam Otto, did to apply autoencoders to this very problem. And it worked pretty well, actually. I mean, autoencoders are a great way of learning, low dimensional kind of state variables that describe a high dimensional system. And it turns out it worked very well for this problem anyway. So I think I think they fit alongside these methods very well.
Can I squeeze one more in now that I have you, Clancy?
Sure.
For the kernel trick in the EDMD, is there any advantage of using, instead of monomials, using like Chebyshev polynomials to get around the overfitting or the more resolution power of orthogonal polynomials rather than just monomials?
Yeah.
Have you experimented with doing the kernel trick with Chebyshev functions or Chebyshev polynomials?
I haven't, and I'm not sure what a kernel is that gives you Chebyshev polynomials. And it may not actually matter if I guess it would give you a different inner product. Yeah, I guess a different. So this feature, I'm just wondering what the feature map looks like. I guess for your feature map, you're thinking map from state space to Chebyshev polynomials of a certain degree.
Yep.
Yeah. And then I'm not sure what the kernel, I guess the difference is the kernel would, the inner product would be different, even though this feature space would be the same space, because you have Chebyshev polynomials of the same degree, same number of variables, would span the same space as monomials, but a different inner product that might be better. So I have not looked at that. I think that's a great idea, though.
Because you said if you put that kernel idea, if you introduce more and more, you get into the overfitting. Well, we know that from polynomial interpolation, but the cure for that one is a different set, right? It's just becoming more and more ill-conditioned. And the way we get around that one is by switching to Chebyshev polynomials. And I was wondering whether that thing actually carries over to your kernel trick.
Yeah, it may well do. I don't actually know. So there's a very easy kernel for monomials. It's just 1 plus x dot y to the power d, if d is the maximum degree. I don't know if there's a corresponding easy kernel for Chebyshev polynomials, but maybe there is, and that could be a really easy thing to try. If so, I will say there are other ways of kind of trying to get at this overfitting problem. I mean, just having a regularization parameter that penalizes, how many say sparsity of your fit. There are tricks like that can be used, but anyway, that's a great suggestion, Peter. Thank you for that. Yeah.
Good. Any more questions from the attendees? Feel free to just unmute yourself and ask. No? All right. Well, thanks again, Clancy. Very nice talk. Very good overview of many different techniques. Super interesting. Thanks a lot.